and welcome to Arithmetica. In this 6th episode of Arithmetica's series on proof and reasoning, we follow on from the previous video of our brief account of abductive inference. In this video, we shall be providing some account of abduction used in mathematics and science. Even though mathematics is largely deductive based, it could be argued that abductive logic has a key role in the analytical process of formulating mathematical conjectures. This includes observed potential structures within the mathematics and from analysing patterns in forming number sequences, etc., as well as those of historical importance, such as Fermat's last theorem, which was technically a conjecture prior its proof in 1994 by English mathematician Andrew Wiles, and subsequent refinement a year later co-written with former student Richard Taylor in filling a gap and thereby providing a complete proof. Indeed, a mathematician can often be inspired from observations in nature as a sort of pattern hunter, in which they might realise some structure sequence, such as the presence of Fibonacci numbers in the number of petals on a flower, as well as the number of spirals formed owing to the arrangement of the leaves around a flower's stem, or that of scales in a pine cone, or of sunflower florets. Such observations has led to forming conjectures as to why this should be. In the case of sunflowers, the florets develop from what are called primordia. The order and arrangement of each successive primordia as they grow outward from the centre of the sunflower head, called the apex, occur at fixed angles, all approximately 137.5 degrees apart. It is this critical angle between successive primordia that leads to the appearance of spirals as they grow outward from the sunflower's apex. The same phenomenon is also present in pine cones, where each new scale is 137.5 degrees from its predecessor. The fundamental link between the mathematics of the Fibonacci numbers and those seen in nature is owing to the presence of an irrational number, often called the golden number, or otherwise called the golden ratio, which is usually denoted by the Greek lowercase letter phi. And the connection between the aforementioned critical angle of 137.5 degrees and the golden ratio is in observing that 137.5 degrees differs from a complete revolution by 222.5 degrees, which is very close to the ratio of 360 degrees to that of the golden number, i.e. 360 over phi, which is approximately equal to 222.49, correct to 2 decimal places. Moreover, the ratios of successive Fibonacci numbers provide increasingly better approximations to phi. Indeed, said ratios tend to phi as we extend through the Fibonacci numbers indefinitely. The critical angle of 137.5 degrees is possible owing to it not being a factor of 360 degrees, thereby allowing a more efficient means of packing the florets into the available space on a sunflower head. Thus, a proposed inference to the best explanation for why the number of spirals of sunflower florets has a tendency to be of a particular Fibonacci number is the mathematical consequence of a natural selection of a good approximation of the golden ratio in order to pack as many seeds as efficiently possible, and of the rate in which the primordia are created as they grow outward from the sunflower head's apex. The golden ratio is often attributed to logarithmic spirals seen in nature, such as seashells and snail shells, Logarithmic spirals are a subclass of the more general concept of equiangular spirals, so called because for any point on their curve, the angle between the tangent of the curve at that point and the radial vector to that point from the center of the spiral is always of the same value. Equiangular spirals are thought to occur in nature when the forces that create them are in equilibrium. Their presence in nature are not limited to living things either. They include the spirals of hurricanes, as well as the spiral arms of a galaxy. The Nautilus Shell has often been associated with the golden ratio, but there has been some question as to whether this should be. If you measure for each stage of a Nautilus Shell's development, then you will likely find that at each instant it has proportions closer to that of a rectangle with a ratio of 4:3, as opposed to the golden rectangle whose proportions, as you might well expect, are of the golden ratio. Thus this implies a constant growth factor of 4/3 per 90 degrees of growth. So the Nautilus shell seems to be best represented by a logarithmic spiral with a growth factor of about 4/3 for each 90 degrees rotation, and not of the golden ratio. But what if we measure not from the center, but from opposite sides of the spiral to those of its outer spirals? Well, as illustrated, we do seem to obtain good estimates of what could be described as being golden proportioned. So, what do you think? Does the Nautilus shell really have golden proportions? Or do you think that it is better described by a logarithmic spiral with a 4/3 growth factor? So, what can we abductively infer from such observations of logarithmic spirals seen, for example, in the Nautilus shell? One possible explanation of equiangular spirals seen in living organisms is, while the specifics of growth can be rather complex, the reason for biological spiral structures are in growing from simple components and in only following simple rules, often including the imperative of maintaining the same shape throughout, thereby providing the most efficient process in attaining the least amount of energy necessary. Consequently, such equiangular spirals seen in biology are often logarithmic, in which the growth of the organism leads to a constant growth factor for the spiral. The presence of the golden ratio as a growth factor thus results in a so-called golden proportioned logarithmic spiral, although, as argued earlier, not all logarithmic spirals seen in biology are necessarily golden proportioned. The somewhat more scientific explanation for the presence of the golden ratio in nature, although mathematical in definition, takes us now to abduction in science. The importance of abduction in science is embodied in the development of a scientific hypothesis, where the scientist is charged with the responsibility of providing a credible explanation or hypothesis for some physical phenomenon or phenomena. By providing an explanation, we can develop a better understanding of the phenomena being observed. Thus, through abductive inference, there is improved understanding. The discovery of more data allows for the returning to the abductive model, in deriving a new and better fit explanation to the observed phenomena. Thus, abductive logic encompasses the very developmental and self-corrective nature of formal scientific disciplines. Indeed, when we consider what was involved in establishing many of the important and much celebrated of scientific discoveries, it is clearly evident that this was not merely a case of intellectual creativity, but conformed to a logical process that was strongly supported by the evidence of or relating to their derivations. Philosophers of science have long argued that abduction is a cornerstone of scientific methodology. This includes Boyd, Hera, Lipton and Psilos. In fact, the Irish philosopher Ernan Macmillan makes the rather bold claim that abduction is the inference that makes science, as the name of his 1992 publication from his Aquinas lecture, as well as the British philosopher Timothy Williamson in stating that the abductive methodology is the best science provides. Such discoveries in which the abductive process has been accredited to includes Pythagoras' explanation for the lunar phases of the moon, in which he argued that the moon was spherical and lit by the sun owing to his knowledge of the effects of light and shadow onto curved surfaces. Simply put, the geometry of the curved surface of a sphere was the best fit to the circular image of the moon in the sky, together with how the phases of the moon changed over time. Another is of the work of Kepler, leading to his famous laws of planetary motion, in which the American philosopher of science Norwood Russell Hanson describes Kepler's discovery as a process of logical inference that was neither deductive nor inductive, but rather retroductive, i.e. of abductive inference, following from empirical measures from celestial observations that provided the most reasonable explanation as elliptical paths for the orbits of the planets that best fits the data. A third example takes us to the beginning of the 19th century, in which observations discovered that Uranus, one of the 7 known planets in our solar system at the time, had an orbital path that deviated from its predicted motion, in accordance to Newton's law of universal gravitation. One possible explanation was that Newton's theory was seriously flawed. However, the predicted path was based on the assumption that there were no other large celestial masses that could influence Uranus's orbit. Also, by this time, Newton's law of universal gravitation and its application in describing planetary motion had provided more than 2 centuries of analytical results, and was supported by the relevant empirical observations. Thus, it was deemed less likely that Newton's theory was at fault, but rather it was the assumption that there was no other masses farther out from Uranus that was to blame, and so it was instead suggested that there was an 8th, as yet undiscovered planet that provided, as one might put it, the best explanation for Uranus's surprising orbit. This explanation of Uranus's deviating orbit was independently proposed simultaneously by the 19th century astronomers John Couch Adams and Urbain Le Verrier in 1845. However, the significance of Adams' calculations was not fully appreciated, while Le Verrier's work was properly recognised. Indeed, only 1 year later, a visual identification of this phantom planet, otherwise known as Neptune, was discovered close to where it had been predicted mathematically by both men. The discovery of Neptune is the first instance when a planet's prediction followed from the mathematics of theoretical science, namely of Newton's law of universal gravitation. Other discoveries that have been accredited to abductive inference include Darwin's theory of natural selection, as well as the aforementioned Newton's theory of gravitation. When we think of the sheer scope of what abductive inference has covered, together with its popularity with scientists and philosophers alike, it is little wonder that it has been described as the logic of discovery. Thank you for watching Arithmetica's brief account of abductive inference in mathematics and science. It is very much hoped that you have enjoyed or perhaps even benefited from watching this video. The next video in this series of Proof and Reasoning will continue our presentation of abduction, where we will provide some of the formal definitions of abductive inference. And so until next time, it's goodbye from Arithmetica!